beginning of chapter 17. So chapter 17 is very much a continuation of chapter 16. So chapter 15 is where it all started, right? We learned about equilibrium, just the basics of equilibrium. We learned about equilibrium constants, how to handle solids, liquids, how to solve using either ice tables or the equilibrium constant expression. We did lots of those. And then in chapter 19, we added acids and bases on top of it, where we talked about how to calculate, well, we learned about the differences between strong acids, strong bases, weak bases. We learned 3 definitions of acids and bases, and then learned how to calculate using those 4 categories. So in chapter 17, with the super specific title of Additional Aspects of Aqueous Equilibrium, is taking all the rest of the equilibrium stuff that we didn't cover in 15 and 16 and shoving it into one chapter. Now this video is called Part 0 because in the spring, when COVID initially hit, the first video that I had to make in the spring was right after this. So what's being called part 1 of chapter 17, because that's just where we were when we needed to pick things up. So for whatever reason, I called it part 1 video, knowing that it wasn't the first part of chapter 17. So we're picking up at chapter 17. Good and bad news. You need to know everything from 15 and 16 to be successful in chapter 17. Okay, so let's start with our beautiful course or chapter objectives. So again, these are the list of the things that you need to know how to do by the end of chapter 17. It's a good thing to look at when you're studying for the exam. Okay, so good news is we're starting with, in some ways, a review. So this is a balanced equilibrium reaction. It's acetic acid, which we would prefer to write it like this because then it's obvious that it is an acid because the hydrogen is out front. But organic chemists like to write it this way because this is the order in which the atoms are attached, and so the hydrogen is at the end. Either way, acetic acid is a weak acid because it's not one of the 7 strong acids, and here it is as its equilibrium equation. Okay, so the solution of acetic acid mixed with water. If we were to add the acetate ion, this, okay, based on the Le Chatelier principle, which we talked about in chapter 15, the reaction would shift to the left, because remember the Le Chatelier principle states that when a reaction was in equilibrium and you screwed with it somehow, these are my words, not theirs, and you screwed with it somehow, the reaction is going to respond by trying to fix whatever you did. So if what I did was added acetate, the reaction is going to try to fix that by using up all that extra acetate, which means going more in the left direction because that's when the acetate gets used up. Okay, so that's just following the Le Chatelier principle. Well, in chapter 17, when this happens, they call it the common ion effect. The common ion effect is just the Le Chatelier principle, okay? So let's go back and look at this again. If I were to add H3O+, so if I poured more H3O+ into my reaction, the reaction would respond by shifting to the left also, okay? So what happens is H3O+ is the correct way to write H+, because we know when H+ is floating around in water, it will always attach itself to a water molecule, becoming H3O+. And this is the acetate polyatomic ion. We're fine. Everything's fine. So the acetate polyatomic ion is this, and the hydrogen ion is this. And so the reason why they call it the common ion effect is we are adding one of the ions in common with the acid that we started with. Okay, so let's look at the words about the common ion effect, and then we'll come back and talk about this some more. So the common ion effect says, the extent of ionization of a weak electrolyte like a weak acid or a weak base, and the extent of ionization in terms of a weak acid or weak base, it means how much it either donates its proton or accepts its proton. So the amount of acid or baseness, these are the fancy words, of a weak acid or base is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So if I had HF as my weak electrolyte, and it's a weak electrolyte because it's a weak acid, if I added something that had hydrogens in it, or if I added something that had fluorides in it, what the common ion effect is saying is that the reaction will shift left, which means more of it will be in the format of the weak electrolyte. So HF becomes a less good acid if I were to add some extra H+, or if I were to add some extra F-. Now, when we're dealing with the common ion effect, I can't go and get myself a beaker of just F minus. That's not possible. In a beaker, we have to have electroneutrality, which means the overall charge has to be 0. So F minus, I can't get a beaker of F minus, but I could get her a beaker of NaF. Now, sodium is not in common with anything. So we don't care about the sodium. What the sodium fluoride would be was a way for F minus to be added to the solution. So I couldn't add just HCl, or sorry, H+, but I could add HCl, which is one of the 7 strong acids. So I know that it would break apart into H+. So what this is saying is if we add an ion that is part of the weak acid or the weak base, so we add one of those pieces, the reaction is going to shift to the left, and the acid or base is going to be less effective. It's not going to be as acidic or basic, which is what happens when it shifts to the left. Okay, so HF was the example that we used here. So I want us to utilize this in, how does this change our calculations? How can we change this? Because we would like to be able to then calculate, well, how much different is it, I guess. So we're supposed to calculate the fluoride ion concentration and pH of a solution that is 0.20 molarity in HF and 0.10 molarity in HCl, and we're given the Ka value. So how this problem is different than Chapter 16, we're given 2 chemicals. In Chapter 16, we were only ever given 1 chemical. You were given a strong acid, or a weak acid, or a strong base, or a weak base. In this problem, we're given 2 chemicals. Now, our first job in Chapter 16 was to look at the chemical and decide which of those 4 things it was. Well, in Chapter 17, we have more than 1 chemical, but that's still our job. We need to look at our chemicals. So HF, I'm calling that a weak acid, okay? Because it's an acid, it starts with H. It's not one of the 7 strong acids, so that makes it a weak acid, okay? And then HCl is a strong acid because it's one of the 7 strong acids that we had to memorize in Chapter 16, and we still have to know in Chapter 17. Okay, so, and here's our other hint. We were given the Ka value for HF. Only weak acids have Ka values. So that's another hint that hydrofluoric acid is a weak acid. Okay, so we have this situation. We've got a weak acid and a strong acid. I want to write my equilibrium equation. Now, my equilibrium equation, I only have one of those. I only have one for HF. Hydrochloric acid is a strong acid. It does not go to equilibrium. So as far as I'm concerned, I could call this HA, right? We said weak acids were HA. So HA. And this, strong acids, isn't their molarity equal to H3O+? That's the definition of strong acids. Okay, so I'm just going to start this. So that was the what type of chemicals are present in this question, the weak acid and the strong acid. So this is me writing like the HA equation, only I put in actually HF. So in Chapter 16, I always did HA. I'm just rewriting it so it would be like this. Okay, so what I want us to do is set up our ice table. We're supposed to solve for F minus, which is this. We're also supposed to solve for the pH, which is going to come from this. Okay, so those are the things that we need to solve for. So when I go to do my ice table, so the HF value, we were told it was 0.20. The H3O+ value, the reason why I put 0.10 there is because HCl is a strong acid, and those 7 strong acids are equal to H3O+. Now F minus, that was not given as an initial value. Now for the change row, there's my squiggly line. Oh, and I ignored water because it's a liquid, okay? Remember in the change row, one side has to be positive changes and the other side has to be negative changes. Well, the product side has to be positive changes because the F minus is a 0, so it has to increase. So I'm going to have minus X, because only 1X because there's 1 HF, plus X because there's 1 H3O+, and then plus 1X because of F minus. So again, the 0.10 number is coming from the 0.10 HCl. We just have to remember, one of the things you had to memorize in Chapter 16 was what are the 7 strong acids, and that their molarity is equal to H3O+. So we're just utilizing that, okay? We were not given in the question any of the equilibrium values. So what I'm going to do is just take the initial row plus the change row and write that down here. Now, we had this shortcut that we learned in chapter 16 about these trailing x's, right? The minus x or the plus x, not the x by itself, but anything after a number. And that had to do with the equilibrium constant. So what I didn't bring on this slide was the equilibrium constant. So I'm going to backtrack. The Ka value is 6.8 times 10 to the negative fourth. Crap. We cannot do the shortcut here because our rule was negative 8 or smaller, times 10 to the negative 8, times 10 to the negative 9, negative 10. So negative 4 is not small enough. So I have to leave those trailing x's. Again, the question is asking for me to solve for this and this. So I need to know the value of x, and I do not yet know the value of x. So what I'm going to do is plop that into the equilibrium constant expression. Okay, so Ka equals the H3O plus times the A minus, which in this problem was F minus, over HA, which in this problem was HF. Okay, so I just took the number or the expressions from the equilibrium row. I'm going to have to distribute the x. I'm going to cross multiply and distribute. I'm going to have to do the quadratic formula. Okay, so I'm just kind of shortcutting my way here. So in this one, for the quadratic formula, A is 1, B is 0.10068, and C is negative 1.36 times 10 to the negative fourth. So we plug that into the negative b plus or minus the square root of b squared minus 4ac all over 2a. Get two values for x. One of them would be positive, one of them will be negative. The one that's positive is 0.0013. So I'm going with that is the value of x. Okay, so we still have to answer the question. So I'm going to plot that back into my ice table. Well, I guess I should backtrack here. 0.0013, right? So F minus is going to be 0.0013. H3O plus is going to be 0.10 plus 0.0013. So then we'll have to calculate the pH. So that's where me saying the F minus is equal to 1.3 times 10 to the negative third. Scientific notation version of the number I just wrote down. H3O plus is equal to that, which I need to use to solve for the pH. So I get 0.99. Now the reason why it looks like this, with addition, we have to go by decimal places. So 2 decimal places, and remember this number is 0.0013. This pen. So 2 decimal places. This number had 4 decimal places. DP, I don't know what SP is. And so our answer needs to have the smallest number of decimal places. So 2 or 4, which one is smaller? 2. So 2 decimal places. Oh, sorry. There, which this, for the pH equation, the number of sig figs inside of the log relates to the number of decimal places for the pH. Well, this has 2 sig figs, and so that has 2 decimal places, so 0.99. This is acidic because the pH is less than 7. So what that's changed, the common ion effect, is just, it's given us more than one initial value. And what we need to know is that based on the Le Chatelier principle, it's going to shift everything to the left. If you add one of the products, then it's going to shift everything to the left. So the big portion of this chapter, it's an important thing at the beginning, and then we're going to use it for the rest of the chapter, is this idea of buffers. Buffers are a topic that you learn in Gen Chem 2, and you're going to be expected to know for any of you going on to quantitative analysis, which is the coolest, but also for all of you going on to biochemistry. So biochemistry is a course needed for biology majors, chemistry majors, pre-med, pre-dental, pre-pharmacy, anyone that's related to any sort of biology thing, you still have to take biochemistry. So biochemistry can be offered as either a biology course or a chemistry course, depending on your institution, but it doesn't matter. They're going to expect that you know what buffers are. Okay, so buffers are a mixture of a weak acid and its conjugate weak base. So like HF and F minus. So a weak acid and its conjugate base mixed in the same solution. Okay, that's how you would to make a buffer, is mix a weak acid with its weak base. And what they do is they are resistant to pH changes. So when we make a buffer, we would make a buffer at a certain pH. So in this picture, there's a blue bottle that says buffer solution pH 10, a yellow one that says buffer solution pH 7, and a red one that says buffer solution pH 4. So those buffers were made by mixing, it doesn't tell us on the front which acid and which base they mixed together. But when they did, they made it to a pH of, I'm going to go with the red one, with a pH of 4. So if we were to take this buffer and some hydrochloric acid would get dropped into it. Okay. Well, hydrochloric acid is one of the 7 strong acids. So as a strong acid, it dissociates completely. It definitely makes things more acidic. So we would see the pH decrease. okay? But in that buffer, the pH would not decrease very much. If instead of dropping the hydrochloric acid in the buffer, we dropped it in water, we would see a very dramatic drop in pH. So buffers, what it means by they are particularly resistant to pH changes. When you add a strong acid or a strong base, the pH doesn't change as much as it would if you added it to water. These are important. So pH, human bodies, certain parts of our body, which is pretty much all of them, are sensitive to pH. Okay, certain pH changes of our blood, very small pH changes of our blood, are enough to kill us. Certain areas of our body are more acidic than others. This is important in the pharmaceutical industry. So if a pharmaceutical company was trying to create a drug that would cure brain cancer, I don't know, making up something, okay, and they found this molecule that would, but that molecule is really, really acidic, okay, and by putting it into the person's body who has brain cancer, it will go and fix the brain cancer, but on its way, changes the pH of the human body so much that it kills you. So the drug is magical because it cures brain cancer, but it kills you before it does that. Those are bad things, right? We don't want that to happen. So buffers are really important, not just at the pharmaceutical industry, but that's one example of why they're really important in biological processes. Most things that are alive are very pH dependent. If the pH changes too much, they're not alive anymore. So buffers are super important. When I used to work at the pharmaceutical testing company that was owned by the University of Iowa, where I worked before I started teaching, I started almost every day by making a whole bunch of buffers, okay, because they were just very, very important, okay? So a buffer is a mixture of a weak acid and a weak base, and what they do is resist pH changes. So how that is important in the pharmaceutical industry is you can add a buffer to that medication, and that would keep that very strong acid, whatever it is, from changing the pH of the body as it moves through there. Keeping the human being alive. These are good things, right? We like that. Okay, so here's a picture that came with our textbook that is supposed to explain how a buffer works. So in this example, the buffer is hydrofluoric acid, a weak acid, mixed with fluoride, which would really be sodium fluoride because F minus by itself is not something we can have. But either way, it's a weak acid and its conjugate base. Okay, so what would happen is if I take, here's my buffer, it's a mixture of HF and F minus, okay? And if I were to add a strong base to it, so I'm just going to pick one of the 8 strong bases, sodium hydroxide. Okay, well, what we have to do here is think a little bit backwards, back into Gen Chem 1. In Gen Chem 1, you learned a bunch of different types of chemical reactions. Okay, you learned combination, decomposition, combustion, blah, blah, blah. There were lots of them. One of those categories was an acid-base reaction. Now, in Gen Chem 1, you didn't learn an acid-acid reaction or a base-base reaction because those aren't reactions. Okay. The only type of chemical reaction that involved acids and bases, a neutralization is a type of this, but are acid-base reactions. So that tells you what chemicals are going to react when they're mixed together. Acids will react with bases. Acids will not react with acids. Bases will not react with bases. Okay, but acids will react with bases. So if I identify all of these chemicals, this was a strong base. This is a weak acid. This is a weak base. So when I mix these 3 chemicals together, 2 of the 3 chemicals are going to react with each other. And by the way, a weak acid and its conjugate base are not going to react with each other because that's 2 forms of the same thing. Okay. So what's going to react here? The strong base is going to react with the weak acid. And when it does that, I could predict the products. Now when I predict the products, I'm not going to use the equilibrium arrow because strong bases do not go to equilibrium. So I'm treating this like a double replacement, a double displacement, a metathesis, whatever word you want to use. H is going to go with OH to make H2O, and Na is going to go with F minus to make sodium fluoride. And so what happens is when we added the sodium hydroxide is going to react with some of the hydrofluoric acids, which is when we look at this picture, the amount of HF, it's kind of like the pinkish orangey color here. At the end of the reaction, the amount of HF decreased because some of it reacted. It's gone now. It reacted with the sodium hydroxide, okay? But if you look at the F minus, the blue one, the amount of F minus actually went up from beginning to end because we made some of it. So in this process, adding a strong base, what it did was the strong base reacted with one of the components of the buffer, the weak acid part, and reacted the strong base to turn it from a strong base into water, which is neutral, and a weak base. So that means that the pH is not going to change nearly as much because we just turned the strong base, neutralized it, left just a weak base. So we still would see the pH increase. We're adding a base, so the pH would go up. But it would not increase nearly as much as if it would if that HF had not been there. So flipping that around, if we added one of the 7 strong acids, so if I have HF, an F minus, a weak acid, a weak base, and I add, that's a B, hydrochloric acid, which is a strong acid. Well, the strong acid is going to react with one of the 2 things in the buffer. It's going to react with the base. Okay, so when that happens, I can, if I want, write NaF, because that's what it would actually look like in there. So the H and the F would go together, and NaCl would be what was left. So when we look at this bracket, or the boxes, the fluoride amount goes down from beginning to end, because the fluoride, which is part of NaF, is decreasing because it's getting used up, it's reacting. Okay, but the HF box goes up because one of the things we make is HF. So the buffer converted a strong acid into a weak acid, which will see a decrease in pH, but maybe like by 0.2 pH units instead of by like 3 pH units or 12 pH units or something. So this is how a buffer works. Now, if either one of these columns, if either the HF column or the F minus column gets all the way to the bottom, to where one of the components has run out, it's not a buffer anymore. It's only a buffer when there's both weak acid and weak base. That would be, well, the buffer is no longer useful. Okay, it's not a buffer. It's just a weak acid or it's just a weak base. So that's when so buffers are not perfect. They don't last forever, is what I'm saying. So looking at buffers. Okay, we're going to do some calculations going with this. So this slide right here should not be new. This came from chapter 16. It's the weak acid equilibrium equation and the Ka expression. So I don't know if you remember, but in chapter 16, I liked to take the negative log of things. So I took the negative log of the H3O plus times OH minus equals 1.00 times 10 to the negative 14th equation to come up with pH plus POH equals 14. I like that better. So what we're going to do is I'm going to take this equation. I'm going to take the negative log of it and turn it into something else. Okay, so I rearranged it a little bit. All I did was it's like I pulled the H3O plus out front, and then I'm going to negative log everything. So when I take the negative log of Ka, I'm going to take the negative log of H3O plus, and I'm going to take the negative log of A minus over HA. So the negative log of Ka is now called the pKa. The negative log of H3O plus, we know that from chapter 16, is called pH. And the negative log of A minus over HA, well, we know that, I'm going to be more specific here, A minus stands for a weak base and HA stands for a weak acid. So I'm going to rearrange this a little bit more, okay? Because typically we're solving for pH in these problems. So I'm just going to rearrange this equation so we're solving for pH. So this, WB stands for weak base, WA stands for weak acid. This is called the Henderson-Hasselbalch equation, and we can use it for buffers. We can actually use it anytime we have weak acid and a weak base in the same container, which is, buffers are weak acids and weak bases. But this lets us not have to do an ice table, not have to do the quadratic formula, not have to do all of that. But it only works if you have both a weak acid and a weak base. Back in chapter 16, when you were given problems where you just have a weak acid, you could not have used the Henderson-Hasselbalch equation because you have to have a weak acid and a weak base. But I would suggest that you start looking for these situations because the Henderson-Hasselbalch equation is so much less work than ice tables. Okay, so let's try this. What is the pH of a buffer? And that word right there is a hint, weak acid and weak base. We just have to confirm that with the chemicals. That is 0.12 molarity lactic acid. Looking at that chemical, I'm going to call that a weak acid because it's an acid, and it's not one of the 7 strong acids. And 0.10 molarity in sodium lactate. Well, sodium lactate. Remember when we were doing the 4 categories of chemicals and weak bases? I was like, they're the leftovers. Well, sodium lactate's not a strong acid. It's not a weak acid because it doesn't start with hydrogen and it doesn't have acid in its name. It's not one of the 8 strong bases, which means it's a weak base. The other clue is lactic acid and sodium lactate look very similar, but one of them had the acid form and one of them lost that. This is lactic acid without a hydrogen replaced by a sodium, which makes it a weak base. So we have a weak acid and a weak base, and these are the only 2 chemicals I have, a weak acid and a weak base. So that means we can use the Henderson-Hasselbalch equation. So, oops, I guess I didn't do it on here. pH equals pKa plus log of weak base over weak acid. So I'm going to plug numbers in. We're solving for pH. I don't know that. pKa is equal to the negative log of the Ka value. So negative log of 1.4 times 10 to the negative fourth plus the log of weak base, that molarity was 0.10, divided by the log of weak acid, that molarity is 0.12. Now, if we look at units, the 0.10 and 0.12, they are both molarity, and brackets stand for molarity, right? So in chapter 16, every time we saw brackets, we had to do molarity. Something that's a little bit different about this equation is the molarities are a ratio of each other. So whatever unit the top number is and whatever unit the bottom number is are going to cancel out, which means in this equation, you could put moles in here instead of just molarity. If you think that's going to screw you up and you don't like it, then just only put molarity. So what I need to do are calculations. Well, both of them involve logs. So I need to look at sig figs and decimal places. Well, this has 2 sig figs, so the answer will have 2 decimal places. These numbers have 2 sig figs, so the answer will have 2 decimal places. So I'm going to grab my calculator and do this, and my answer should have 2 decimal places. And I forget that it doesn't show up. What I got to 2 decimal places is 3.77. That would be the pH of this buffer. So I could still ask questions like, is this acidic, basic, or neutral? Okay, this is acidic. So what I'd like for you to do is read this problem, try it. When you're done, hit pause. When you're done, hit play, and we'll go through it together. So the problem says calculate the pH of a buffer consisting of benzoic acid, which is a weak acid, and sodium benzoate, which is a weak base. So I can use the Henderson-Hasselbalch equation. So when I do that, pH equals the pKa. Well, I was not given the pKa, I was given the Ka. So I'm going to have to take 6.3 times 10 to the negative fifth and take the negative log of it, plus the log of the weak base, which is the sodium benzoate, divided by the log of the weak acid, which is the benzoic acid. So my answer is going to have 2 decimal places because all of these numbers had 2 significant figures. And when I did my math, I got 4.42, saying that this buffer is acidic. Aren't Henderson-Hasselbalch equations lovely? Okay, we're almost done. The last thing, well, 2 things, I guess. One is just kind of a definition thing. I told you the buffers are going to be important and that you're going to be expected to know about buffers when you get to higher level chemistry and biochemistry classes. One of those things that you're going to be expected to know is that buffers work at the pH where the acid has its pKa value. So if you're trying to find a buffer that you can make that'll have a pH of 5.5, like you want it to stay consistent at the pH 5.5. So to decide which chemicals you need to mix together, what you need to do is you need to find an acid whose pKa value is 5.5. So in our appendix D, that appendix that's in the back of chapter, or that we use in chapter 16 that's in the back of the textbook, that's listed with the Ka values. Well, lots of textbooks don't list Ka values, they actually list pKa values because it helps with this. So acids work best at the pH that's the same as their pKa value. So that's where the buffer works best for those acids. Okay. And then the last thing we have to do is, how do I handle what happens when I take the buffer and then I add a strong acid or a strong base to it? You know, because like buffers resist the change in pH, but how could I figure out what that pH is? This makes no sense to me. Like these flowchart things are not helpful to my brain, but if they are helpful to you, it's absolutely correct. It's wonderful. But what I'm going to do now is we're going to approach it, I guess the way that I handle these. Okay. So this is the steps that go with the picture. First, it says to calculate the moles of weak acid and weak base in the buffer and the strong acid or base that's added. Because what we're going to do is we're going to have our buffer and then we're going to add either a strong acid or a strong base to it. Then we're going to subtract the moles of strong acid or base from the appropriate component of the buffer and add to the other component. And then use the Henderson-Hasselbalch equation to solve. Okay, so let's do it, and I think it helps when we do this. Here's my problem. A buffer is made by adding some amount of acetic acid, and I know it's an acid because it starts with an H. It's a weak acid because it's not one of the 7 strong ones. And sodium acetate, which is going to be a weak base because it looks like acetic acid, only the hydrogen is gone and replaced with a sodium, with enough water to make 1.00 liters. I was really nice and I already calculated the pKa value. So it's not the Ka, it's the pKa. We're supposed to calculate the pH of this solution after 0.020 moles of sodium hydroxide, which hopefully you recognize as a strong base, is added. So the reason why this problem is going to be different than the last two we did is this is not just weak acid and just weak base. There are three chemicals here: weak acid, weak base, and strong base. So in order to do this calculation, we can't jump into the Henderson-Hasselbalch equation because I have too many kinds of chemicals. So we're going to have to go back and think about the thing we talked about when we looked at the bar graphs about buffers. So what happens is, in this scenario, I've got acetic acid. I have sodium acetate. Oops, C2H3O2. And we have sodium hydroxide. Okay. So I want us to predict what's going to happen. That's a W. I'm just reminding us what chemicals we have. Okay, so the strong bases are going to react until they can't anymore. The strong base is going to have to react with the acid, okay, because acids react with bases. So I'm going to rewrite this equation. This is what's actually going to happen. So the H and the OH are going to make H2O. The sodium and the acetate are going to make sodium acetate. And this is the reaction that's going to happen. So in chapter 17, you are going to have to remember things from Gen Chem 1, like predicting products from balanced equations. This equation is not at equilibrium because we have a strong base. So here's my suggestion. This cannot be an ice table because it's not at equilibrium. So what I'm going to do, it's called a before and after table. This is how I handle these. When I have too many chemicals, we're going to do a before and after table. Before and after tables have to be in moles, not molarity. That's a big difference between ice tables and before and after tables, because in this one, it's not at equilibrium. It's not going back and forth. It's reacting like we have to have a limiting reactant and stuff. And when we did stoichiometry back in Gen Chem 1, we had to get things to mole ratios, so we had to get them to moles, is basically what happened. So what I'm going to do is I'm going to go back and look at the problem, and I need to figure out how many moles of the chemicals there are. Well, luckily the problem actually gave us that. It told us there were 0.300 moles of this chemical, 0.020 moles of this chemical, and 0.300 moles of this chemical. Now, water is not mentioned. Just like before, water, it's neutral. I don't need to keep track of it. Okay, so that's the before. That's how much we started with. Now, what's going to happen? Our two reactants are going to react. They're going to react completely until the limiting reactant is gone. So what we have to do is decide which chemical is the limiting reactant. Well, the limiting reactant is the one that there's the least amount of. So we got to look at the numbers. 0.300, 0.020. Well, 0.020. So what's going to happen is they're going to react until 0.020 moles have gone. And this is a product. So when it reacts, we're adding it. So what's going to happen is at the end, there's going to be less acetic acid than we started with. The sodium hydroxide is completely gone. And there's going to be more sodium acetate than we started with because it got produced. So we have changed our buffer. Our buffer amounts have changed. But the question is asking for the pH. So we got to look at what type of chemicals we have. Well, we have a weak acid. We have a strong base. We had water, which is neutral. We have a weak base. So at the end, the only chemicals that are left are this chemical and this chemical, right? The sodium hydroxide is gone. There's 0 amounts. So there's weak acid and there's weak base. Hey, we can use the Henderson-Hasselbalch equation for this because the weak acid and the weak base are all that's left. So here's the Henderson-Hasselbalch equation. So the pH is equal to, the pKa was actually given in the question, was 4.74, plus the log of weak base, 0.320 moles, divided by weak acid, 0.280 moles, where the unit moles will cancel out because they're on top, it's a ratio. And when I go to do my calculation, this has 2 decimal places, this has 3 sig figs. My answer is going to have 2 decimal places. So what it's going to be is 4.80. So the buffer became more basic because we added sodium hydroxide, which is a base. Now, if you looked at this and you're like, dude, that had brackets. There's brackets, there's brackets. You put in moles, that's wrong. Then yes, you could take your moles and divide them by the volume, which in this case was 1.00 liters. And then molarity divided by molarity would cancel. Since it's a ratio, that's why we're allowed to put moles in here. But that's the only time you can put moles into any of our calculation equations is the Henderson-Hasselbalch equation, and only because it's something divided by something, only because it's a ratio.